Hello and welcome to our session, Unlocking the Lakehouse with Efficient Data Pipelines. My name is Prabodh Bhargi. I am a senior lead data engineer at Capital One. And in my role at Capital One, I am a lead engineer and an architect on our enterprise data platform teams.
Hey guys, Usman Zubair, if you guys can hear me. I'm a lead technologist at Databricks. I've been here for about 5 years, about 2 decades of data experience. I've been working in different capacities with Capital One for the last 4.5 years. It's been a great learning experience and happy to share some of those insights that I've learned over the last 4.5 years and helping them build the ultimate, what I call the ultimate lakehouse.
Thank you, Usman. This is the agenda for today's session. I'll walk through a brief background of Capital One, some of our challenges and objectives as we build our lakehouse. So we'll go over our road to the lakehouse. Then we'll have a deep dive into how we build or how we unlock the lakehouse by building efficient data pipelines, and efficient is the keyword here. Usman will go over our methodology and how we identified the challenges, how we came up with the efficiency metrics. Then I'll wrap up with some key takeaways and learnings through our journey, and then I'll share the road ahead for Capital One's Lakehouse. Capital One, Fast Company's most innovative companies of 2023, has long been a pioneer in using data for strategic decisions. Ever since our first client, customer, and credit card back in 1994, we have recognized that data can enable even the biggest organizations like Capital One to be innovative, yet personalized. With data as our foundation, we embarked on an ambitious tech transformation journey around a decade ago. And this slide provides you some of the key highlights of our tech transformation journey. And you can see here, if I can get my pointer, 2016, we made an ambitious declaration of moving out of our on-prem data centers and going all in on public cloud. And we were able to complete that ambitious goal in around 4 years, which is quite remarkable. And this has been the foundation for our successful Lakehouse implementation. 2023 was the year when we embarked on evolving our existing Lakehouse to version 2 by adopting open table format, which is Delta Lake. This slide provides some sense of scale of Capital One. And while I don't think anybody would be surprised by these numbers, I would like to set the stage and provide an overview of the scale at which Capital One operates. We at Capital One operate a petabyte scale data lake. And the data volumes in our lake is to the tune of hundreds of petabytes. Terabytes of data, and I repeat, terabytes of data is loaded to thousands and thousands of data sets in our lake every single day in near real-time ingestion fashion. Thousands and thousands of users across Capital One consume data from our unified lake. And these users are across job profiles like data scientists, data analysts, data engineers, machine learning engineers, AI engineers, so on and so forth. Building this petabyte scale data lake had its own challenges that needed to be solved. As we set out to evolve our Lakehouse architecture last year, we worked backwards from our goals. And the challenges that we saw in the existing system have influenced our goals. Some of the key challenges, and which naturally became the objectives for our version 2, are poor query experience. Now, this challenge was twofold. The user experience of consuming data from the Lakehouse was poor. And the performance of the queries themselves that were consuming this data from the Lakehouse was poor. So, ensuring a highly performant and extremely good user experience was a key objective for us. However, at the same time, we also wanted to be cost efficient. The existing ecosystem had limited support for advanced use cases. Things like ensuring the atomicity of data or implementing merges, deletes was a huge challenge for us, and it required super complex implementation. So, enabling advanced use cases on our evolved version 2 Lakehouse was a key objective for us. The combination of these two challenges led to data silos. This was in the form of teams owning and managing their own data marts and lake houses outside of our unified lake house, or teams duplicating and copying data into other systems which had easy SQL-based consumption options. As the scale grew, the system also started becoming difficult to maintain. So providing a simple, easy to consume, and a unified lakehouse, which was also scalable to sustain the data volume growth for years to come, was one of the key objectives for our lakehouse. Delta Lake, with its out-of-the-box support for things like ACID transactions, change data feed, time travel, better reliability, resiliency, easy updates, deletes, etc., was a natural choice for the open table format for our lakehouse. Now let's take a look at our reference lakehouse implementation architecture. On the left, we see multiple data ingestion options. We have enabled a platform-managed data ingestion pipeline, which allows our data producers to publish data in near real time in an event-driven fashion, as well as in batch mode by publishing files to our platform-managed pipeline. This platform-managed pipeline also enforces governance rules like schema enforcement, schema evolution, data standardization, data tokenization, lineage capture, etc. Additionally, we have also enabled a self-managed data publishing pipeline. And as the name suggests, it is a self-managed, the producer or a publisher-managed pipeline, which allows the producers to completely own the data publishing pipeline to our lake. The self-managed data publishing pipeline is also complete with the same data governance rules enforcement as our platform-managed data ingestion pipeline. And better yet, it is completely automated. You cannot see the box on the bottom because of the live translation, but the self-service or self-service portal allows us to automatically build the data ingestion pipelines and the data governance rules based on the technical and business metadata. And I would highly recommend you all to attend my colleagues Kajal and Jim's talk tomorrow. You build your data. I think it's at 11:20 tomorrow. They're going to talk about in detail about how Capital has enabled the self-service capabilities. Coming back to the architecture, providing a flexible, governed, and automated publishing option is one of the key enablers of our successful Lakehouse architecture. The data published by the producers is then stored in our unified Lakehouse in Delta Lake format. Choosing an open and extensible format that allows interoperability and allows the consumers to consume data using a tool of their choice is second key enabler for our successful Lakehouse architecture. The operational metadata is for all of our Lakehouse is stored in our operational and technical data catalog, and the business metadata is stored on our custom enterprise business metadata catalog. On the right, we see flexible data consumption options for our variety of user personas. Providing flexible consumption options for our users to consume the data from the unified lake and avoid duplication of data using a tool of their choice is the third key enabler of our successful Lakehouse architecture. As we proved our version 1 of the Lakehouse architecture, we are already looking at the long-term sustainability of the platform. As with any software development process, there were growing pains in our architecture. Some of the challenges that we observed as well as anticipated were challenges of scale. As our version 1 or version 2 of our Lakehouse architecture proved to be successful, we saw an exponential growth in the volumes of data loaded to our new Lakehouse architecture. The system that we have built lacked versatility. It lacked versatility to support the diverse data sets that were loaded using this platform. And the diversity of data sets that I'm talking about are 3 classic V's of big data: volume, variety, and velocity. The jobs that were running on Databricks and were processing data and publishing to our unified lake had a simple batching logic. We were submitting jobs to Databricks clusters in a round-robin fashion. And we were using interactive clusters, and interactive clusters, as you may all know, are long-running clusters as opposed to the ephemeral job clusters. These multiple interactive clusters that we were using had a single job configuration. So that is where the lack of versatility comes into picture. The combination of these two challenges led to underutilization of compute and high operating costs. The team spent a lot of time in supporting data backlogs due to slow running process. This was because of, again, the first two challenges that I mentioned. We did not have the versatility to tune our Databricks compute infrastructure in line with the size of the incoming data. So because of the simple batching and the simple batching algorithm and the limited ability to configure the size of the clusters, we used to face data backlogs when we had sudden spikes in data load. Using interactive clusters also led to some other weird issues, like sometimes our driver memory used to get full and we had to recycle the clusters, which led to additional burden on our support teams. So how did we optimize our data load process, and how did we enable and scale our Lakehouse architecture? I'll invite Usman to cover that part.
So we had a problem, right? Our costs were going, were getting extremely high. We knew there were some knobs that we could turn, but we wanted to really kind of understand that when we rolled this V2 out, we had all the bases covered. We wanted to keep costs under control. We wanted to keep costs predictable. So as Prabodh mentioned, right, the lowest hanging fruit was, okay, we're using all-purpose clusters. It's not a best practice. We should move over to job clusters, right? That would have given us job clusters that are lower cost than all-purpose clusters. That would have given us provisioned compute for our process. So right now we were processing, let's say, hundreds of data sets on that all-purpose clusters in a given hour. So job clusters would have given us dedicated compute. It would have given us ability to troubleshoot much easier because you have a finite number of processes running on that job cluster. But there was one fundamental problem that we really needed to dig deeper and solve, and that was cluster utilization. How do we ensure, and we knew that our clusters were massively underutilized, how do we ensure that a given compute, whether it's 5 nodes or 10 nodes or 2 nodes, that is actually processing the max amount of data for the compute that's been spun up, right? That is essentially the holy grail of making our process uber efficient, right? So we came up with a methodology, right? We wanted to figure out how do we get to that holy grail. So what we did was we came up with a few different configurations that we wanted to test. So based on different compute sizes, and we've kind of left the exact compute size out for confidentiality, but the idea was that we came up with different configurations, different compute sizes. So think of like a 2-node cluster, a 4-node cluster, an 8-node cluster. And then we thought about data volumes, right? So I want to process 10 gigabytes of data in a given batch. I'm going to process 40 gigabytes of data. And that data could be split over a single data set. That data set could be split over 10 data sets, right? Does that matter? So these are some of the different things that we thought about testing. Now, if you think about how Capella One, or if you think about any ingestion, right, just regardless of Capella One, right, an ingestion request could be consisting of 10 records, and it could be consisting of 1 million records, right? So one size cannot fit all, right? You cannot just say, okay, I'm going to just, on the same compute cluster, I'm going to ingest 10 records, and on the same one, I'm going to ingest 1 million records, right? What's going to end up happening is that when you do the 10 records, you're going to waste a lot of compute. And the other problem is, if you bring up compute just to process 10 records, yeah, there's an overhead there. It takes time to spin up compute. You're going to waste a lot of resources, and that's going to really spike your costs. Now, the overall objective, while we were testing these different configurations and trying to get to that sweet spot, was We want to ensure that our processing time of a pipeline is within 5 minutes, because that was our business SLA. We have to complete, but from the time that the ingestion request came in from a producer, we wanted that data to be ingested, regardless if it was 40 gigs or 10 records or whatever the size was. We wanted that to be completed within 5 minutes. So that was our underlying SLA from a timing standpoint. So, as we were testing what the right compute specs needed to be for a given amount of data, we also wanted to ensure that costs were proportional. And we came to the realization that if we have the right spec size for a cluster for the right amount of data, that our costs are going to be directly proportional to the amount of data processed, right? And we want our costs, right? I think if you take one thing back today is that you want your costs for processing data to be either linear or sublinear. You do not want them to be exponential, right? So you don't want your costs to grow exponentially as your data volumes increase, because your data volumes will always continue to increase. So after trying out a few combinations of different data sizes and compute sizes, we were able to find that sweet spot, right? So if we take 2 gigs of data and we put it on extra small compute size, we're going to get our 5-minute SLA, right? So we were able to find that consistency, and then from there we knew that if our data kept on increasing tenfold, we knew exactly which compute size we need to process that data within that 5-minute SLA. Now, another metric that Capital One used, right, as part of this evaluation and this testing, and they continue to use to really kind of make sure that their pipelines are cost efficient, is cost per process GB. And the idea there is that if I have the right compute size for the right amount of data, if I am fully utilizing my compute resources, my cost per process GB will be very consistent. It'll be very predictable. So what we realized there is that if I give, for example, in this case, a tiny cluster, which is, let's assume that's a 2-core cluster. If I give that cluster too less data, my cost per GB is going to be much higher. So I don't want to be in that place. I want to be where that flat line is, right? I want to be at a place where I know exactly what my cost is as my data scales out. So in this example, this 2-core cluster could process up to 250 megabytes, right? Now, if I give it less than 250 megabytes, then I'm leaving some money on the table, essentially. So what does this all lead to, right? So once we were able to get to that sweet spot, so we had two different things that were happening here. We had to figure out the right compute size for the right amount of data, which is we just talked about. But there's another factor here where we had to build an orchestration mechanism which intelligently groups incoming requests. So I'm producer 1, I want to ingest 10 records. I'm a producer 2, and I have 1 million records, right? So those requests all come in at the same time. We can't control that as a platform. So how do we compile those requests intelligently? How do we orchestrate them and ship them to the same job cluster? So that, for example, if all that data compiles to, let's say, 40 gigs total across 10 data sets, I know exactly how much compute I need to spin up. I submit those processes, all those 10 data sets, totaling 40 GB on that compute size, and then the output is I get that processed, I get that ingested within 5 minutes. Now keep in mind, right, any metrics that we talked about today, they're very specific to Capital One, right? They're not gonna hold true to every single situation, because in Capital One's case, as Prabodh mentioned, we're not just ingesting data, we're not reading and writing, we are tokenizing, we are checking schema, we're doing data quality, we're doing all kinds of data quality checks and standardization on the data before it goes into the Lakehouse. So again, it also varies what DBR version you use, whether you use Photon, you don't use Photon, what instance types you pick. So there's a lot of different configurations that obviously we didn't kind of put on the slide. So just keep in mind that the important part here is the methodology we use, right? We knew we had to increase utilization on our clusters. We knew that was a problem, and we came up with what seems like a very simple thought process, but it really helped us get to that factor. And that really led to north of 60% reduction in our overall compute costs for our ingestion pipelines. And I think when we talk about scale, we had this slide up earlier. When we talk about scale, this is all about Capital One's ability to scale their Lakehouse ecosystem. It's about improving latency as business requirements change, right? So today it's 5 minutes. Tomorrow there could be use cases that want this data within a minute, within 10 seconds. If we can be predictable with our cost, we know exactly how much time it takes with X amount of compute, with Y amount of data, we can scale that out. There's no limit, right? Because we're working with the cloud economies of scale. So with that, I'll pass it back to Prabodh to cover some of the key takeaways.
Thanks, Usman. So we've seen the architecture slide, and I talked about the 3 key enablers for our successful Lakehouse architecture. I would like to add or share some of our key learnings and the takeaways as we went through this process, as we evolved our Lakehouse architecture, and more importantly, the optimization that we did in our pipelines. Shouldn't surprise anyone, Usman covered this in detail. Always optimize your compute utilization. With the cloud economies of scale, compute has become a supremely accessible resource. With that, it is also easy to just spin up or over provision and underutilize your compute. Thank you so much.
Thank you.